Run your fingers through your hair right now. What you are touching is not just a style choice. Every strand on your head is a biological structure engineered by evolution, stronger than copper of the same size, shaped by climate, and designed for protection, insulation, and survival. Your hair type is not cosmetic. It is ancient climate technology. And researchers recently discovered that every strand may also store a hidden record of your biological history. By the end of this video, you will never look at your hair the same way again. Now let's start with straight hair and the advantage most people overlook entirely. If your hair falls flat from root to tip without bending, you are carrying the most efficient oil distribution system of any hair type. Your scalp produces an oil called sebum from tiny glands attached to every follicle. Sebum is not just a cosmetic annoyance. It is a protective coating that waterproofs the strand, locks in moisture, prevents microbial infection of the scalp, and shields the hair shaft from UV-induced protein degradation. On a straight strand, sebum faces no obstacles. It slides from root to tip in a continuous film, coating the entire length evenly. This is why straight hair tends to develop a natural shine more quickly after washing. That shine is not vanity. It is light reflecting off a uniform lipid layer, and it signals that the strand is fully sealed and protected. Curly and coily hair types have to fight gravity and friction at every bend in the strand to move that same sebum downward, which is why those textures tend toward dryness at the ends. Straight hair solves this problem with geometry. The strand is a frictionless highway for its own protective coating. There is another advantage buried in physics. A straight strand lying flat against the scalp creates minimal air resistance and minimal tangling between adjacent strands. This means less mechanical breakage from daily friction, less force needed during combing, and less cumulative structural damage over time. In regions with high humidity and heavy rainfall, where waterproofing and low maintenance were survival priorities rather than style preferences, straight hair offered a tangible, functional edge. Now, if your hair bends into loose S-shaped waves rather than falling completely straight, you are sitting on a structural compromise that gives you something neither straight nor curly hair achieves on its own. Volume without extremes. Wavy hair creates natural lift at the root because the bend in each strand pushes it slightly away from the scalp and away from neighboring strands. This lift traps a thin layer of air between your hair and your skin. That air layer functions as insulation, which may sound insignificant until you consider the thermal engineering involved. In temperate climates with variable seasons, where temperatures swing between hot summers and cold winters, a flexible insulation system is more useful than a fixed one. Straight hair lies flat and offers minimal insulation. Tightly coiled hair creates dense insulation that is constant. Wavy hair adjusts. When the air is dry and cool, the waves tighten slightly, trapping more air. When humidity rises, the waves loosen and expand, increasing airflow to the scalp. This is not deliberate, it is physics. The protein bonds in wavy hair are more responsive to moisture-driven expansion and contraction than either extreme. Wavy hair also distributes sebum better than curly or coily types while still maintaining enough texture to prevent the rapid oil buildup that straight hair experiences. It strikes a middle ground that handles the widest range of conditions with the least amount of biological intervention. Researchers studying the global distribution of hair types have noted that wavy hair appears with high frequency in populations from Mediterranean, Middle Eastern, and South Asian regions, areas defined by seasonal temperature variation and intermediate UV exposure, exactly the conditions where a flexible system outperforms a specialized one. If your hair coils into defined spirals or corkscrew shapes, you are wearing one of the most effective UV defense systems biology has ever produced, and a landmark study has finally explained exactly how it works. In 2023, researchers at Penn State University published findings in the journal eLife that fundamentally changed our understanding of why curly and coily hair evolved. The study used thermal mannequins, human-shaped models equipped with precise heat sensors, fitted with wigs of varying curl patterns and exposed to controlled solar radiation. The results were striking. Tightly curled hair reduced solar heat gain to the scalp by a significantly greater margin than straight hair. But the mechanism was not what most people would guess. The advantage was not about thickness or density, it was about architecture. Curly hair does not lie flat against the head. It creates a three-dimensional canopy that stands off the scalp, forming an air gap between the outer surface of the hair and the skin beneath. This air gap functions as a buffer zone. Solar radiation heats the outer hair surface, but the trapped air beneath acts as an insulating barrier, preventing that heat from conducting directly into the scalp and the blood vessels beneath it. Straight hair, by contrast, lies directly on the skin and transfers solar heat almost immediately. The researchers concluded that tightly curled hair likely evolved as a thermoregulatory adaptation in equatorial environments where direct solar radiation on the scalp could elevate brain temperature to dangerous levels. Your curly hair is not just protecting your skin, it is protecting your brain. There is an additional advantage at the molecular level. Each bend in a curly strand creates a structural stress point where the protein bonds are compressed on the inside of the curve and stretched on the outside. These stress points make curly hair more elastic than straight hair. A curly strand can stretch up to 50% beyond its resting length before breaking, while a straight strand typically breaks at a lower extension threshold. This elasticity makes curly hair more resilient to mechanical shock, sudden pulling forces, and physical impact, which may have offered a protective advantage during active pursuits in dense vegetation and rough terrain. If your hair grows in tight coils or zigzag patterns with very little hang length, what is often classified as type 4 hair, you are carrying the most thermally advanced hair architecture in the human species. Everything the Penn State study found about curly hair applies to coily hair in an amplified form. The tighter the coil, the greater the standoff distance from the scalp, the larger the insulating air gap, and the more effective the heat shield. But coily hair adds another layer. Because the coils are so tight, they interlock with each other, creating a dense mesh that functions almost like a woven fabric above the scalp. This mesh does two things simultaneously. It blocks a higher percentage of incoming UV radiation than any other texture, functioning as a natural broad-spectrum sunscreen for the most sun-exposed surface of the body. And it maximizes evaporative cooling. When you sweat, moisture from the scalp wicks into the base of this mesh, where the large surface area created by thousands of interlocking coils accelerates evaporation. Evaporation pulls heat away from the skin. This is the same principle behind cooling towers in power plants, and coily hair replicates it on a biological scale. The evolutionary logic is powerful. In equatorial Africa, where modern humans originated and spent the vast majority of our species' history, the primary thermoregulatory challenge was keeping the brain cool under extreme solar load while remaining physically active. Coily hair solved this problem so effectively that it became the default hair type for the majority of human evolutionary history. Straight hair emerged much later as human populations migrated into northern latitudes where UV protection became less critical and sebum distribution for waterproofing became more advantageous. If you have coily hair, you are not wearing a deviation from normal. You are wearing the original engineering. Everything else is the adaptation. Now, beyond curl pattern, there is a second dimension of hair type that carries its own hidden advantages. Strand thickness. If you have ever compared a single strand of your hair to someone else's and noticed a visible difference in diameter, that difference is not cosmetic. It is structural engineering. A thick strand of hair, common in East Asian populations and measured at roughly 80 to 120 micrometers in diameter, contains a larger medulla, the hollow core running through the center of the strand. This larger core gives thick hair greater rigidity and compressive strength. It resists bending and holds its shape under mechanical stress. This is why thick, straight hair can support elaborate structural styles without chemical reinforcement. It is also more resistant to environmental weathering. UV radiation, wind erosion, and chemical exposure degrade the outer cuticle layer of the strand, but a thicker strand has more cuticle layers to lose before the structural cortex is compromised. Thin hair, common in northern European populations and often measuring between 50 and 70 micrometers, sacrifices structural strength for density. Thin-haired individuals typically have significantly more follicles per square centimeter of scalp, sometimes exceeding 120,000 total strands compared to roughly 100,000 for thick hair. More strands means more total surface area for sensory detection. Each hair follicle is surrounded by a network of nerve endings that detect pressure, vibration, and airflow. Research has shown that these follicular nerves are sensitive enough to detect the displacement of a single strand. A scalp with 20,000 more sensory units spread across its surface is processing a denser field of tactile information. This may seem trivial until you consider that scalp sensitivity contributes to spatial awareness, thermoregulation feedback, and even threat detection. You may have experienced this yourself. That strange feeling when someone is standing too close behind you, or the subtle prickle when a breeze shifts, is partly your follicular nerve network processing changes in airflow across your scalp. Here is where the science of hair takes a turn that most people never see coming. Because beyond texture, curl pattern, and thickness, your hair is doing something that no other external tissue on your body does. It is recording. Every strand of hair growing from your head is a biological timeline. As the strand grows, roughly 1 centimeter per month, it incorporates trace elements from your blood supply into its protein matrix. These elements are locked in permanently. They do not wash out. They do not fade. When forensic scientists or clinical researchers analyze a strand of your hair, they can read it like a core sample drilled from a glacier. A 12-centimeter strand contains approximately 12 months of biological history. Researchers can detect cortisol levels embedded in the strand, creating a month-by-month map of your stress exposure. They can identify nutritional deficiencies from specific mineral ratios. They can detect hormonal shifts, including pregnancy, thyroid dysfunction, and metabolic changes. A study published in Psychoneuroendocrinology validated hair cortisol analysis as a reliable long-term stress biomarker, superior to blood or saliva sampling because it captures chronic exposure rather than a single-moment snapshot. But the recording goes even deeper. The ratio of oxygen and hydrogen isotopes in your hair changes based on the water you drink, which varies by geographic location. Forensic researchers have used this to trace the travel history of unidentified individuals, determining not just where someone lived, but when they moved between regions. Your hair is not just growing, it is writing a diary. Every strand on your head right now contains a compressed record of where you have been, what you have eaten, how stressed you have been, and what your hormones have been doing for the past several years. No other visible part of your body stores this kind of longitudinal data. So the next time you look in the mirror and see hair that is too flat, too frizzy, too thin, too thick, too curly, or too straight, understand what you are actually seeing. Tell me in the comments, what is your hair type and what surprised you most about what it was engineered to do? And if you have spent years fighting your natural texture, leave a like for the science that says your hair was right all along.